Heisenberg. What we're going to do is look back at a conventional way of looking at physics. Let's take Newton's laws. The laws of motion, for example, and classical mechanics. These pretty much worked in the same way. You got the equation, you put the numbers in, and you got the definitive answer. There was no question about what the answer was. The numbers you put in, you got exactly the right answer that you were looking for. So there was certainty in whatever was going on because you knew the mathematical equation or the mathematical formula which described the behavior you're looking at, and you were able to get the answer. Then in the 20th century, determinism basically died. The death of determinism. The world isn't like the way Newton described it and Galileo described it. There's no definite answer. Things are a bit fuzzy, things are a bit vague. Particles behave like waves, waves behave like particles. Waves behaves like matter. Matter behaves like waves, taking de Broglie. Matter is a little bit fuzzy, a little bit. Matter can be described not by exactly what it is or where it is, but by a probability function as described by Schrödinger. In other words, certainty has been replaced by uncertainty. And this brings us to Heisenberg. Outline the Heisenberg uncertainty principle with regard to position, momentum, and time energy. Okay, let's have a quick recap. Light has a dual nature. It's a wave. It can demonstrate interference, diffraction, and so on. But it also behaves like particles, like photons, demonstrating the photoelectric effect. We call this the wave-particle duality for light. And let's look at de Broglie's hypothesis, which is the dual nature of matter. A particle with a momentum has a matter wave, a wave association with it, whose wavelength is given by his equation, which is lambda is equal to h over p, Planck's constant divided by the momentum. And this is a key point to the uncertainty associated with the wave of this. So let's look at this. Radiation is E is equal to hf. Matter is the wavelength is equal to h over p. Each has a dual nature. Now let's look at a particle. Our traditional understanding of a particle is that it's fixed, it has hard edges, and it's well defined. And it has definite position, definite momentum, and it's confined in space. And our understanding of a wave is that it's diffuse, it's not defined. It's delocalized and spread out in space and time. But we know particles behave like waves and waves behave like particles. So they can have also part of each other's properties. This is a wave packet, a way of looking at a photon, is that this is a wave and the photon is in here somewhere, represented by this wave. We don't know exactly where it is, but we have what's called a wave packet. The uncertainty of finding the position, delta x, is the size of this wave packet. So we have an uncertainty in locating this quanta, this photon that's in this wave packet. Now let's look at Heisenberg's thought experiment, his microscope. Herr Heisenberg was looking through his microscope to find precisely the location and the momentum of an electron. Now it was quite dim, he couldn't see very well, so he had to turn up the brightness to see the electron better, to get a more precise idea of its position. So by turning up the light, he was able to see the electron more clearly. The problem was that the more he turned up the brightness, the more photons hit and bounced off the electron, and they gave it momentum, and therefore it started to move around much more than it was before. So he was able to shine lots of light on it to see precisely where what its position was. But the more he found out more precisely his position, the less precisely he knew the momentum, because he was giving it lots of energy. And it's like, the more you precisely try to look for something, the more you change what it is you're looking for. Now, Heisenberg's uncertainty principle is this. The uncertainty principle is an important consequence of the wave-particle duality of matter and radiation, and is inherent to the quantum description of nature, particle and wave properties. And this is his principle. It is impossible to know both the exact position and the exact momentum of an object at the same time. And this is a fact of nature. The more precisely you know its position, the less precisely you're going to know the momentum. On the other hand, if you know the momentum precisely, the less precisely you will know the position. Here's an analogy. We have a car which is going to pass past this window with a momentum, and we measure the momentum by finding out the time it takes to go across, and then working out its speed, and then you can work out the momentum. So let's see what happens when the car moves across now. You saw it pass. Okay, the car just went past the window. Now, when it was here, there was some kind of uncertainty in its position at any particular time. It was somewhere in this area. Okay, so you know its position fairly precisely. What about the speed? Well, if you measure the time at the beginning and time at the end, and you know the distance, you can work out the speed. But it happens so quickly, you're not able to very clearly define the time that it takes to go across. If you can't define the time, you can't define the speed or the momentum. So you might be able to find out the position fairly precisely, but the momentum is going to have a great deal of uncertainty. On the other hand, if you have a larger window and set up such that you can measure the time from here to here, you can get a better idea of what the speed is, because these two intervals, these two moments in time here are quite a time apart, quite a distance apart. So you can measure the speed quite accurately, but you know at some point during its passage past the window, it's going to be in here somewhere. So the uncertainty in the position is high, the uncertainty in the speed is going to be much smaller. So here we go. So it was easier to measure the starting and finishing time, and therefore the speed and hence momentum. But when it's in this area, the uncertainty in the momentum is quite high. And this is what Heisenberg said. You can't know the momentum and the position precisely. The more precisely you know one, the less precisely you're going to know the other. And he expressed this using this equation. The uncertainty in the position is delta x. The uncertainty in the momentum is delta p, and it's got a subscript x because it means along in the x direction. So delta x, delta p is going to be greater than, this is the uncertainty in x, and the uncertainty in the momentum in the x direction is going to be greater than or equal to h divided by 4 pi. And it's not just a comparison between the uncertainty in position and momentum, it's also the uncertainty in energy and time. If you have a particle which is able to exist and it has a certain amount of energy for sure, it's going to, the bigger the amount of energy that it has, the smaller the time that it can exist for. And this will also be greater than h over 4 pi. To give an example, you recognize this? Probably not. What it's supposed to represent is a nucleus with protons and neutrons together. Now, you know that there's an electrostatic force pushing the protons apart. They have to be overcome by the strong nuclear force which is pulling the protons and neutrons together. Now, the strong nuclear force is carried by a particle which has mass. So the exchange particle has a certain mass, or rather a certain amount of energy, because E is equal to mc squared. But this is going to be a virtual particle. We're not going to be able to detect it because it's basically going to be exchanged between two of these, which enables this force to exist. So this exchange particle is only able to exist if we're not able to detect it, so it has an uncertainty E. Now we know what the mass of this particle is, and it's got quite a large mass. So if this is going to be quite large, the energy is going to be quite large. It must mean that the length of time that it can exist for is going to be quite low. So this has got as the energy, the mass of this exchange particle increases, the time for which it can exist must go down. And this is why this particle, which carries the strong nuclear force, cannot exist outside the nucleus. It has a mass, so it has an uncertainty in the energy, which is only going to be occurring inside the nucleus. If the exchange particle for the strong nuclear force is able to travel for a long distance, it would take a long time, but we only know that it can exist for a very short time. This exchange particle does not have time to be able to go outside the nucleus. In other words, the range of the strong nuclear force is only within the nucleus. It can't exist outside the nucleus because it doesn't have enough time to get there. It will be absorbed or decay before it gets outside the nucleus. Force carrier, which has mass, will only have a limited range. The electrostatic force, however, which doesn't have a mass, can have a very, very low energy because it could have a very low frequency, and that effectively has an infinite range because the uncertainty in energy can be zero, which means that the delta T can be an infinite number, which means that the photon, this low energy photon, could have an almost infinite range. And that's how we know the electrostatic force works. So we have these two conjugate variables, position and momentum, and energy and time. And this is another way of looking at it, is that we've got delta x and delta p, the uncertainty in x, the uncertainty in p, in this wave packet here. The uncertainty of finding the position is quite small here, but it means the uncertainty in the momentum is going to be quite large. On the other hand, if you know that the uncertainty in the position of this photon is really quite large, it must mean that the uncertainty in the momentum is going to be small. Heisenberg's uncertainty principle, in the syllabus it says, students should be aware that the conjugate quantities, position, momentum, and time energy cannot be known precisely at the same time. They should know of the link between the uncertainty principle and the de Broglie hypothesis. For example, students should know that if a particle has a uniquely defined de Broglie wavelength, in other words, there's no uncertainty in the wavelength, then there's no uncertainty in the momentum, because the wavelength is equal to h divided by the momentum, which means the momentum is known precisely. And if this is known precisely, the uncertainty of the momentum is zero. It must mean that the uncertainty in x is infinite. Here we have a question. A beam of electrons is coming from the left, has a wavelength lambda, and is incident on the aperture of height d. The beam is travelling on in the x direction, and the height d is the same order as lambda. Okay. After passing through the aperture, in other words, and some time after the aperture, the component momentum in the x direction, in that direction, is px, and the momentum in the z direction is pz. Which of the following shows the uncertainty in px and the uncertainty in pz? Now, you know that after it goes through, where could it be after this point? In the x direction, it could be anywhere at this position. So what is the uncertainty in x? Well, the uncertainty in x is very large, which means the uncertainty in the momentum in the x direction is going to be very small, and it could be zero, so it would be either A or B. On the other hand, what is the uncertainty in z as it comes through in the z directions. The uncertainty in the position, can't be anywhere in this range. It must be somewhere in this range, which is the size of d. We're told that the wavelength is the size of d. So the uncertainty in the position is lambda. We also know that this is going to be lambda here is equal to the uncertainty in the momentum is equal to h divided by 4 pi. So we divide both sides by lambda, and we have the momentum, the uncertainty in the momentum of the electron in the z direction is h divided by 4 pi d, or 4 by lambda. So it's going to be the answer is going to be B here. Here we have another question. The graph shows the variation with distance of the wave function psi of an electron at a particular instant in time. So you know the electron is in here somewhere. The electron is confined within a region of length 2 times 10 to the minus 10 meters. So it's somewhere in here. Whereabouts it is, we have no idea. We just know it's in here somewhere. So what is the uncertainty? The uncertainty is the distance from there to there. That's the uncertainty in its position. So from this, you need to find out the uncertainty in the momentum using Heisenberg's uncertainty principle.
Welcome. Today I'm really excited because we get to talk about part 2 of quantum mechanics, another part of quantum mechanics, and that is the Heisenberg uncertainty principle. All right? And I got my nice tricked out little green car to help us talk about it. All right? So the Heisenberg uncertainty principle talks about two things, all right, in combination with each other. And that is that you cannot know exactly where something is and how much momentum it has at the same time. There's a limit to how much you can know of either one. All right? And for purposes of discussion today, we're just going to consider momentum to be just velocity, or how fast it's going. All right? And so what we're saying is you cannot know how fast something is going and exactly where it is at the same time. There's an upper limit, and you just can't know. If you know really well how fast something's going, you can't know really well where it is. And there's sort of two ways to talk about it. One way is very quantum mechanical, another way is very conceptual. We'll start with the conceptual way. We got a little test car, and let's see if we can figure out exactly where and how fast this car is going. So we start off screen, zoom, there goes zooming by, and look, zoom, it can zoom back the other way. It's great fun. Can do it all day. All right, so we have our car. Figuring out where a car is not too bad. All right, so the location will be here, all right, or the location could be there. But that's straightforward, but it's not always clear how do you figure out how fast the car is going. All right, so what we're going to do is we're going to take the car, and it's going to come along, and if it comes in on the screen here, right, we can time and see how long it takes to go and go off the screen right over here. All right, and so the time it takes to go in and off the screen will tell us, that's a certain amount of time, we can take the distance it moved and divide it by the time it took, right, and that gives us a velocity. So then we know how fast the car is going, right? Here we go. Whoa! All right, that's great. And depending on the size of the screen you're watching on, that could be a really fast velocity, or if you have like some ginormous billboard, you're projecting this on Yankee Stadium's billboard or something, that could be, I guess that'd be a faster velocity. Yeah, so if you have a tiny screen, it's a really slow, right? And look, it's really speeding now. All right, so if you think about this starts to make sense that we can't really know the position and the velocity, right? Because we needed two locations in order to calculate the velocity, all right? And so since if this is cards going really fast, all right, it will be difficult for us to take two measurements really close together. All right? And if we take two measurements really close together, we will know that it traveled from here to there with a certain velocity. And at that velocity, we knew the car was right on here. Well, if it's going really fast, we could widen, all right, our measurement, and we'll get a better, more accurate reading about how fast it's going. But now we've lost track of like just where it is. And so you can kind of see that there's always going to be a limit, right? It's either going to be a really wide window that we time its velocity, and then we won't know where it is. Or if we do a really narrow window and watch its velocity from here to there, all right, if we that's not going to get a very accurate velocity because all the errors in the experiment are not going to crop up. All right, and so that's conceptually what we're talking about with the Heisenberg uncertainty principle, but it's not really why it happens. Okay, the real reason is quantum mechanics. So stay with me and let's just talk a little bit about why that happens. So the problem comes in because we're thinking about the car as one solid object. Which, yes, it is, but in quantum mechanical terms, okay, everything behaves also like a wave, and that's where the uncertainty principle comes into play and really can be explained a little bit better. All right, so it's not one solid particle, which, you know, this is a solid thing, but it also has wave-like behavior. All right, that's a wiggly thing, right? Some wiggly thing, like you throw a rock into a pond, you see the waves going out. All right, you know what waves look like. They're long and wiggly like that, okay? So you can see you would run into trouble if you're starting to think about things in terms of waves. You can have a tall, thin wave, right? And then you know exactly where the wave is, but you're not going to know its wavelength very well because you want to have a bunch of waves to kind of measure like how long, what's the regularity of it. You just got this one peak. You don't really know where does it start, where does it end, and all that sort of thing like that. So you have the same sort of problem coming in that we had with our car. Right? We can know where it's at, but it's hard to find the velocity. When we have waves, we can find a wave and make it really sharp and know exactly where it's at, but we're going to have a hard time finding its length because it doesn't repeat over itself. You want to measure wavelengths from the peak of one to peak another. Okay, if you spread it out, you can get a really good wavelength, all right, and that help you decide like where it, how fast it's going, all right. But if it's all spread out like this, it's kind of hard to tell just where the wave is, and so you're always running into this problem. Where is it and how fast it's going, and you have this limit, and that's called the Heisenberg uncertainty principle. You multiply the momentum times the position, okay, the accuracy of those things, and that will turn out and give you this number. You can never get greater than that number, okay? It's smaller than that number, more precise, okay? And so that will keep you from finding too much information out. And this is a good thing, because quantum mechanics will actually break down if this is not true. Okay? Basically, no one has ever come up with an experiment where you can know position and momentum to more accuracy than is allowed by the Heisenberg uncertainty principle. And if someone could come up with an experiment that would do that, it would cause all kinds of problems in quantum mechanics, right? Because they would all fall apart. But since no one's been able to come up with an experiment that will do that, we're pretty sure that this is a good way to go. It's the way we understand things. Now, to end it off, we got one more cool thing, and that is that the Heisenberg uncertainty principle can also be done with different dimensions than momentum and position. You can also do it with energy and time. And this is what I love, okay? Because of this, a vacuum is not empty. Get that? Right? I'll say it again. Because of this, a vacuum is not empty. So we go to outer space where it's practically a vacuum, almost nothing there. Okay. What happens is the Heisenberg uncertainty principle can also be applied to energy and time. And what that says is you can have particles come out of nowhere. Okay. So you have nothing, and then boom, you have something. All right. And that's a particle that appeared out of nowhere. All right. But the limit, though, is that the more energy this particle has, the shorter the lifetime of that particle. And then you're satisfying the uncertainty principle here, right? Because technically that says is that you have this limit of energy and time relationship, so if it doesn't exist very long, you can't really measure its energy. And so you basically, in outer space, in a vacuum, you can have things appear and disappear again really fast, and so that's the time portion. And if it disappears fast enough, you can actually have a particle of a certain amount of energy. Now, this is not going to create a new universe or do anything really wacky. It's too hard to measure for all but the most sensitive experiments. It's not going to mess up your science fair project or something like that. All right? But if conceptually, I love the fact that in space there are particles that are just appearing and disappearing really fast all the time. Okay? And so empty space is not really empty. So take that with you as you go. And until next time, where we might talk about other cool quantum mechanics things, remember, you, my friend, are a wave.